So how do we actually get an electromagnetic wave or a radiation? Now, to discuss about this, so we have Ampere's circuitry law, right? See, Ampere's circuitry law, it was not consistent for certain circuits. Like, suppose let's say we have a capacitor. Now, a charged capacitor has a conduction current, right? Now, for two surfaces, let's say S1 and S2, if we are actually applying Ampere's circuitry law, it's not going to give us the proper wave or the proper magnetic field. Now, how? We'll see. Okay. So, see, consider these two surfaces. Let's say surface S1. Now, it is bounded by loop L, right? Here, the conduction current I, it is going through that particular surface, right? So, by Ampere's circuitry law, what we have is we have to take the line integral of the magnetic field along the loop, right? So, we have integral of B dot dl is equal to mu naught into I. This is for surface 1. Now, for surface 2, the same thing, it is also bounded by loop L, but no current is passing through it, correct? Right? So, what happens? Integral of B dot dl is equal to mu naught into 0, which gives us 0, right? But if you look at it, the left hand sides of both the equations are the same, but right hand side they are not the same, correct? Because one is giving us mu naught into I, another was giving us 0. So here Ampere's circuitry law, it was logically it was not consistent, like we could not make out whether this is true or false, right? Now, so one person, James Maxwell, like I told, James Maxwell, he came and he modified the Ampere's circuitry law. Alright, how he modified was he introduced a concept called as displacement current. So this displacement current plays a very important part. Alright, so let's see what is that displacement current. Displacement current is basically, see, it's the current which is between the two plates. Now, whenever we have a charged capacitor, one current passes through the outside circuit, that is from one plate to another plate, that is basically conduction current. Alright. Now, between the two plates, what Ampere assumed was there was no current which was passing through that. But what Maxwell did was, he kept a small magnet between the two plates, and the magnet showed a deflection. That means there is magnetic field, and like what we have studied in the previous chapters, the change in magnetic field induces current, right? So that inducing current is what we call as displacement current. Okay. So now the Ampere's circuitry law, this guy came and he modified it, correct? So how he modified was B dot dl is equal to mu naught into IC plus ID. Here IC is the conduction current and ID is the displacement current. Now this formula, which is mu naught into IC plus ID, is what we call as modified Ampere's circuitry law or Ampere-Maxwell's circuitry law. Okay. So here, see, the displacement current arising, why is it arising? Because of the varying magnetic field, right? So we can write ID is equal to epsilon naught into d phi divided by dt, the change in flux. So our modified Ampere circuitry law will change to integral of B dot dl is equal to mu naught into IC plus epsilon naught into d phi by dt. So this is what we have as Ampere-Maxwell's circuitry law. Okay. So what is displacement current? It is the current arising due to the varying electric field in between the plates of capacitor. So using the displacement current, we arrive at an equation B dot dl is equal to mu naught into IC plus epsilon naught into d phi by dt. So this is how Maxwell came and how he introduced the concept of displacement current.